In this video, we'll discuss the Bezout identity, which is the following. Given two natural numbers, m and n, then we can always find integers a and b such that a times m plus b times n equals the greatest common divisor of m and n. So this is a theorem. We'll say why it's true, and we'll give an efficient way, an efficient algorithm to compute these a and b for a given m and n. The first remark I can give now is that a and b are not unique. Let's start first with a few simple examples. So if I take, for example, m equals 7 and n is 9, in this case I know that the greatest common divisor is, of course, 1. Now Bezout's identity says that there should be a and b such that a times 7 plus b times 9 equals 1. So in this case, let's see, we can guess and try. So we realize quickly that 4 times 7 plus negative 3 times 9 in fact equals 1, because this is 28 and this is negative 27. Now those numbers 4 and negative 3 are not unique. I can add 9 to this one and negative 7 to this one and get another pair of numbers a and b such that the identity is true. So let's see. 13 times 7 plus negative 10 times 9 also equals 1. It's easy to check. This is 91 and this is negative 90. Another example, say m equal 8 and n is 30. In this case, the greatest common divisor is 2. Now I want integers a and b such that a times 8 plus b times 30 equal 2. So here as well it's easy to see that if I take a equal 4 and b is negative 1, then the answer is obviously 2. So we want to see why it works always, and we want an efficient way to find a and b for any given m and n, which might be very, very, very large. And it's important to have an efficient method to do it because, as we'll see later, if you want to calculate modular multiplicative inverses, which is something that your computer or your smartphone does all the time, the numbers m and n are very large, as we say, something of the order 10 to the 600. So numbers with around 600 digits. And you cannot guess and try. You'll never be able to do it this way. This will be done using the Euclidean algorithm. So the Euclidean algorithm tells us why the Bezout identity is true, why a and b exist, and how to find them efficiently, quickly. So as in the last video, I want to use the Euclidean algorithm to compute the greatest common divisor of m and n. Suppose m is greater than n without loss of generality, and m, I call it a0, n, I call it a1. So I divide a0 by a1, I have a remainder a2, and then I divide a1 by a2, I have a remainder a3, and so on, till I get to a remainder which is 0. And the greatest common divisor is the last non-zero remainder. And what I want is to write a n plus 2 as a times m plus b times n, where a and b are integers. How can I do it? I cannot do it in one step, so I'll do it in several steps. The first step, I look at this last equation. From this equation, I can write the greatest common divisor, which is a n plus 2, as something times a n plus some other thing times a n plus 1. And I write down here, a n plus 2 is 1 times a n plus negative qn times a n plus 1. This is not yet what I want. I want a n plus 2 as something times a0 plus some other thing times a1. And I'll get there in the following steps. The next step is to get rid of this a n plus 1. And I do it by considering the above equation. So looking at this equation, I can write an plus 1 as an minus 1 plus negative qn minus 1 times an. Now I can regroup the terms in an and the terms with an minus 1. So in an minus 1 I have negative qn times an minus 1 plus 1 plus qn minus 1 times an. So until now I have that my greatest common divisor is something times an minus 1 plus some other thing, some other integers times an. But I don't want that. I wanted something times a0 plus some other thing times a1. Now I look at the equation just above and I get rid of the an. The an, I replace it with an minus 2 minus qn minus 2 an minus 1. And when I do this step, I'll have the greatest common divisor written as something times an minus 2 plus some other thing times an minus 1. And then I use the equation before. I get rid from the an minus 1. So I got the GCD something times an minus 3 plus some other thing times an minus 2. And so on till I get to the first line. And once I get there, I have then my GCD written as something, some a times a0 plus b times a1 for some integers a and b. So a times m plus b times n, because m I called it a0 and n was called an a1 for some coherence in our notation. So stop the video, think about it a little bit, and convince yourself that works. Let's do an example where we don't want to guess the coefficients, we just want to calculate them. So say, take m equals 15, n equals 41, and the question is find a, b, and z such that a times 15 plus b times 41 equals the greatest common divisor of 15 and 41. Perhaps we don't know it, this greatest common divisor. It's 1 in fact. We'll calculate it anyway. So we start, I divide the largest one by the smaller one. So I write 41 is 2 times 15 plus 11. Now I divide 15 by 11. So 15 is 1 times 11 plus 4. And now I divide 11 by 4. So 11 is 2 times 4 plus 3. Now I divide 4 by 3. 4 is 1 times 3 plus 1. Okay, great. Now the 1 is the last non-zero remainder, of course, because if I divide 3 by 1, 3 equals 3 times 1 plus 0. The greatest common divisor is this one, clearly. So now I'm looking for a and b such that a times 15 plus b times 41 equal 1. Okay, good. So I start with the last step, which tells me that 1 can be written as 4. I write it 1 times 4 plus negative 1 times 3. The 3 here is this one here. And this, on the line above, was a remainder. So when I use the line above, I can get rid of this 3 and write it as a combination of 4 and 11. So I write 1 equal 1 times 4 plus negative 1 times, instead of 3, I use this line, I write it 11 minus 2 times 4. And now when I want to regroup, I want to keep the 4 here and keep the 11, because 4 and 11 are one of those remainders which appeared. So I regroup the terms with 4. I have 1 times 4, and here I have a negative 1 times minus 2 times 4, so it's 3 times 4 plus negative 1 times 11. So I've written 1 as a combination of 4 and 11. 4 and 11, but I don't want that, so I get rid of the 4 using this, and then I get rid of the 11 using this, and then I'm done. So using this second line, I write 4, instead of 4 I can write 15 minus 11, or plus negative 1 times 11, and here I have plus negative 1 times 11, and this equals 3 times 15 plus negative 4 times 11. And now I use the first line to get rid of the 11. 3 times 15 plus negative 4 times 41 minus 2 times 15. Of course, I want to keep the 15 and the 41 because that was my question in the first place. So I write everything negative 4 times 41, and with 15 I have 3 times 15, and here I have 8 times 15, so it's 11 times 15. And that's all. I wanted a and b such that a times 15 plus b times 41 is 1. Well, here they are. I take this is a and this is b. Indeed, 11 times 15 is 165, and 4 times 41 is 164. And indeed, it is 1. Let's make another example. So find a and b such that a times 63 plus b times 40 is the greatest common divisor of those numbers, which is 1 in fact. So stop the video and try to make the calculation yourself to make sure you know how it works, because it's a little bit confusing in fact when you go up the Euclidean algorithm. At a given step you don't want to get rid of the wrong number. So let's see. I start by dividing. So 63, I write it 1 times 40 plus 23, and then I divide 40 by 23. 40 is 1 times 23 plus 17. Now I divide 23 by 17. 23 is 1 times 17 plus 6. Now I divide 17 by 6. 17 is 2 times 6 plus 5. 6 is 1 times 5 plus 1. 5 is 5 times 1 plus 0. So indeed, the greatest common divisor is 1. First, realize how the 23 in the first step was a remainder, and the second it was a divisor, and third it was a dividend. The same holds for the 17. Here it's a remainder, divisor, dividend. The same for the 6 and for the 5. And all those numbers, which appear in squares, together of course with the two most important numbers, these ones which appeared already on the statement of the problem, those are the important numbers for us. So I want to write this one here as something times 63 plus some other thing times 40. I cannot do it in one step. So the first step I write 1 is, using this equation, 6 minus 5, which is 17 minus 2 times 6. And now this is negative 17 plus 3 times 6. And you don't want to make the calculation here, because of course if you do it you'll get 1. 3 times 6, you keep it 3 times 6, you not write it 18. Why? Because it's in the next step. Using the above line, you'll get rid of the 6 by writing 6, instead of 6 you write 23 minus 17. And now you have something, 1 is written 3 times 23 minus 4 times 17. And indeed it's the case. 3 times 23, if you check the calculation, this is 69, and this here is 68. The difference is 1, it should be 1. Now we want to get rid of the 17 using the second line, so I write 17 as 40 minus 23, and this is then negative 4 times 40 plus 7 times 23. So far so good. That's negative 160, and that's 161. The sum is 1, as it should be. I use the first equation, and I write 23 as 63 minus 40. So I get minus 4 times 40 plus 7 times 63 minus 40. And all this gives 7 times 63 plus, so negative 11 times 40. And this is indeed 1 if you make the calculation. And we answered our question, this question, by taking a equals 7 and b is negative 11.